Hello, in this video we're going to introduce the concept of simple harmonic oscillator. We will learn why simple harmonic oscillators are important for mechanical and electrical engineers. Then we are going to derive the equation of motion describing the dynamics of a typical simple harmonic oscillator. Then we are going to solve this equation of motion analytically, and we are going to analyze the solution. Before I start, I have to mention that I have created a post that describes everything that I will tell you in this lecture. This post consists of equations, of graphs, and everything is nicely written. So my advice is to basically combine this lecture with the information given in this post. A link to the post is given in the description below this video. So, over here, you can see a typical example of a simple harmonic oscillator. This is a mass and a spring system. So you can imagine a body of a mass M that is attached to the wall by a spring. So here is the spring. And if we displace this object from its equilibrium position, so here is the equilibrium position, what will happen? The object will oscillate. So if this is x, the x is the displacement of the object from its equilibrium position, and this is time. And if you set certain non-zero displacement, you will see a sinusoidal behavior. So the displacement will oscillate around its equilibrium point. So our first goal is to derive a differential equation that describes this motion, and then we will derive a method for solving such equation. And finally, we will analyze the solution. As always, the first step is to derive a free body diagram. This is always the first step. So here is a free body diagram of the object. Fs is the force that the spring is exerting on the object, mg is the weight of the object, and n is a vertical reaction force from the ground. We are assuming that the surface that you cannot see over here is frictionless. So you can imagine this is basically a box standing on an ice plate or on a frozen lake. Then the second step is to apply the second Newton's law. So let us apply the second Newton's law. We can write mass times the acceleration equals sum of all the forces acting on this body, but this is not exactly body. This is basically, in our approximation, this is a material point. So we have general forces Fi. Now, let's see what are the forces. We have Fs plus mg plus n. Notice that this is a vector equation. The signs are not taken into account over here. The next step is to introduce a coordinate system. So we're going to measure the displacement of the object from its equilibrium point, and this will be the x-axis. So let us project this equation onto the x-axis. So we can write m x2 dots. X2 dots is it's the second derivative of the position vector equals minus Fs and nothing more. On the y-axis, we have m y2 dots is equal to, we have to denote the y-axis, is equal to n minus mg, and this is equal to 0, since the object is constrained on the plane, doesn't move in the y direction. So we don't need this equation. We only need this equation. Now, spring force Fs is equal to K, which is a spring constant times the displacement x. By substituting this equation into the first equation, we obtain mx2 dots is equal to minus kx, or we can write this equation as x2 dots plus k over mx is equal to 0. Now, this term over here, k over m, we are going to introduce a new notation for this term. We are going to introduce omega n, and omega n is going to be a square root of k over m. This parameter, omega n, is a very important parameter in mechanical and electrical engineering. It is called a natural frequency. So this is a natural frequency. You will see later in the video what is the physical meaning of this parameter. So the equation can be written x2 dots plus omega n square x is equal to 0. So this is our equation of motion. This is a second order differential equation. Why is it a second order? Because the highest derivative is of a second order. This is a linear differential equation. Why is it a linear differential equation? Because the unknown variable x enters linearly in the system and x2 dots enters linearly in the system. So this is our equation of motion. Its solution is a function x of time. Its solution basically is the displacement as a function of time. Our next goal is to solve the equation of motion. In order to solve this equation of motion, we need to introduce a trial function. So this trial function will have the following form. It's going to be exponential function s times time, where s is a complex number. So s in general case is a complex number. Now, by substituting this trial function into the differential equation, we obtain s squared e to the st. So basically we are taking the second derivative of x. We obtain something like this, plus omega n squared times e to the power st, and this is equal to 0. Now we can factor out e to the power st, so we have s squared plus omega n squared e to the power st is equal to 0. Now, when these two terms, when their product is equal to 0, either e st is 0 or s squared plus omega n squared is equal to 0. E to the power st cannot be equal to 0. Then the only possibility is that this term is equal to 0. So by solving this quadratic equation, we obtain the solution that has the following form. S12 is equal to omega n times I plus minus, where I is an imaginary unit. So I is square root of minus 1. So this is our solution. This equation is called an auxiliary equation, and the solution of the ordinary differential equation will be a weighted sum of two functions. So the solution will be x of t, where t is time, will be c1 e2, the first root, omega n I t, plus c2 e2 omega n I t with the minus sign. We don't like the complex number or the imaginary unit in this equation, so we will simplify this equation in the sequel. So, in order to simplify this equation, we will use the famous Euler formula. The Euler formula is saying that e to the phi I, where phi is an arbitrary number, is equal to cosinus phi plus imaginary unit times sinus phi. So let us apply this formula to this equation. We can write x of t is equal to c1 multiplying cosinus omega n t plus I sinus omega n t. This is the first term. The second term becomes c2 cosinus of minus omega n t plus I sinus of minus omega n t. Now, since the cosinus of omega minus omega n t is equal to cosinus of omega n t, and sinus of minus omega n t is equal to minus sinus of omega n t, we can write x of t is equal to, we group the terms. We are going to group cosinus and sinus terms. So we can write c1 plus c2 multiplying cosinus omega n t plus, we group the terms that are multiplying the sinus. It is I multiplying c1, and from this term we are going to have minus c2 sinus omega n t. Now, these two constants, c1 plus c2 and c1 minus v2, we are going to simply introduce new constants. So this will be k1 and this will be k2. So our solution has the following form: k1 cosinus omega n t plus k2 sinus omega n t. So this is our solution. Our goal is to further simplify this expression. So we want to write eventually this expression as x of t is equal to an amplitude times a sinus function of omega n t plus certain phase angle theta. This is what we want to do, since we can easily sketch such a function. So here is the trick. Now, in trigonometry, there is a famous additive formula. So sinus alpha plus beta is equal to what? Do you remember the expression of sinus alpha plus sinus beta? Well, I do. So sinus alpha plus beta is equal to sinus alpha cosinus beta plus sinus beta cosinus alpha. So let us apply this formula to this expression. So we can write a sinus omega n t plus theta is equal to A. Now our alpha will be omega n t, so let us just write down, it's sinus omega n t cosinus beta, beta is equal to theta, plus sinus theta cosinus omega n t. Now, let us compare this expression with our solution. So, we can observe that K1 is equal to, so I forgot here an A, right? K1 is equal to A sinus theta. K2 is equal to A cosinus theta. Now, from these two equations, we want to express theta as certain function of K1 and K2, and we want to express A and the amplitude as a function of K1 and K2. So let us do that. If we take squares of both equations, we can obtain K1 square plus K2 square is equal to A square sinus square theta plus A square cosinus square theta. We know that sinus square theta plus cosinus square theta is equal to 1. So we have that K1 square plus K2 square is equal to A square. So from here, A is equal to square root of K1 square plus K2 square. Now, how to find theta? If we divide these two equations, we can obtain K1 over K2 is equal to sinus theta over cosinus theta, or tangents theta is equal to K1 over K2. From here, we obtain that theta is equal to arc tan of K1 over K2. And we were able to express A and theta in terms of K1 and K2. Finally, let us solve a simple example. Let us assume that initially the position of the harmonic oscillator was 0 and that the initial velocity was equal to 1. So graphically, this means that the object is in its equilibrium position, so this is the equilibrium position, and it moves in the positive x direction. So it has some initial velocity. Definitely it will move in this direction and it will return and it will oscillate. So let us now substitute these values in the solutions. So what do we have? The general solution has the following form: C1 or K1, we use the notation K1 cosinus omega n t plus K2 sinus omega n t. So let us substitute the first initial condition. So x of 0 is equal to 0. So what do we have here? We have K1 cosinus omega n times 0 plus K2 sinus 0 is 0, and this is equal to 0. So from this equation, since the cosinus of omega n is omega n times 0 is basically equal to 1, we have K1 is 0. Now, we got rid of the constant K1. So let us substitute the second initial condition. So x dot of 0 is equal to 1. If you take the first derivative while taking into account that K1 is equal to 0, we have x dot is equal to K2 times omega n times cosinus omega n t. And this should be equal to 1 when t is equal to 0. So let us substitute the value. So we have K2 times omega n times cosinus omega n times 0. is 1. This term is equal to 1. So we have K2 is equal 1 over omega n. So our solution has the following form. X of t is equal to K2, it's 1 over omega n sinus omega n t. So this is our amplitude of oscillation. This is the angular frequency of the oscillation. So the angular frequency is equal to 2 pi times the frequency in hertz, and t is time. There is no phase angle. So graphically, our object will oscillate like this, according to the sinusoidal function. So let us analyze the solution closely. So the general solution is given by x of t is a times sinus omega n t plus certain angle theta, or in our case, for the particular case we got, it was 1 over omega n sinus omega n t, where the omega n is square root of k over m. This term is called the natural frequency. So, what can we conclude from this expression? First of all, we see that the frequency of oscillation does not depend on the initial conditions. It only depends on system properties. It depends on the spring constant, how stiff is the spring constant, and it depends on the mass of the object, right? Higher the stiffness of the constant and lower the mass, the frequency of oscillation will be faster. So here you can see a relatively fast oscillations. For this, m is small, k is large, and for this case, generally speaking, for the second case of oscillation, you can see that m is relatively high and k is relatively low. So mass is usually a measure of inertia of the system. So higher the mass, lower the oscillation are going to be. Higher the mass, smaller the oscillations, right? It means the larger the period of oscillation. You can also express omega n as 2 pi over t, where t is basically period of oscillation. The next thing that we can notice is that the amplitude, right? The amplitude is very important. In our case, here the amplitude will be 1 over omega n. So the amplitude will in some way depend on the natural frequency, which is already determined by the proportion of k and m. As a final step, we want to verify that our solution is correct. So how to do this? This was our original differential equation. So how to verify that the solution that we derive for certain initial conditions is actually the correct solution? Well, this solution has to satisfy the differential equation. So let us verify. So the second dot, first dot of x is 1 over omega n times cosinus omega n t. Now, these two terms cancel each other, so we have x 2 dots is minus omega n sinus omega n t. So by substituting x 2 dots and x of t, we obtain minus omega n sinus omega nt plus omega n squared times 1 over omega n sinus omega nt should be equal to 0. So let us see. We can see that square here and the term here cancel each other, and we have minus omega n sinus omega nt plus omega n sinus omega nt is equal to 0. So it's okay. Now, you can also verify that this is a solution by numerically computing the solution using the approach that I explained in my previous video. So using MATLAB to solve this equation, and then you can plot the function 1 over omega n sinus omega nt, and you can plot the MATLAB solution, and then you can see that this is basically the correct solution. Thank you very much for your attention.